The work-energy theorem is an extremely important principle in physics and used frequently in energy analysis. What it states is that net work is equal to the change in kinetic energy, which I will call K here. So this work refers to net work, which can be written like this, or as the sum of all the work done in an object. Net work can be found either by finding the work done by the net force on the object, or by adding all the work done by the individual forces on an object. Work is a scalar quantity, as work is the dot product of force and distance. So these are vectors, and work is the dot product. And since it's scalar, it means that you can add it directly and do not need to apply vector rules. However, work can be either positive or negative, and that depends on whether something is doing work on an object or if the object is doing work on something else. And so the magnitude of work can be written as, well, since it's scalar, it only has magnitude, but work is equal to the magnitude of force times the magnitude of distance times cosine theta, where theta is the angle between two vectors. So like this angle here would be theta. Now, in a one-dimensional case, we can prove that work is equal to the change in kinetic energy when there is constant acceleration. So work in one dimension can be written as work is equal to force that's parallel to distance. So in this case, it means that the components of the force and distance vectors are parallel, which is basically the same as saying the dot product. Now, remember that force is equal to mass times acceleration. So we can rewrite this as work is equal to mass times acceleration times distance. Now, if you recall the kinematic formulas, you know that one of them states that for constant acceleration, the final velocity of an object, we'll call it Vf squared, is equal to 2 times acceleration times displacement plus the initial velocity of an object squared. Rearranging this, we find that acceleration times displacement is equal to the difference of the final velocity squared and the initial velocity squared over 2. Now, displacement here can be written as distance if we assume that the acceleration is constant and the velocity doesn't flip signs. So that means that this is equal to AD. So now we can substitute this in for the work equation, and that gives us that work is equal to mass times Vf squared minus V0 squared, or this can be Vi, that's just a notational difference, divided by 2. And distributing this out, we get work is equal to 1/2 mVf squared minus 1/2 mV0 squared. And noting that kinetic energy is equal to 1/2 mv squared, it's quite clear here that we have shown that work is equal to the final kinetic energy minus the initial kinetic energy, which we'll call Ki. And this is then equal to the change in kinetic energy. So this proves that the work-energy theorem holds in cases with constant acceleration. Now, we can show that the work-energy theorem also holds in cases with variable acceleration. But to do that, we will require knowledge of calculus. So we can either do that by working from work and going to kinetic energy, or we can start off with kinetic energy and prove that it's equal to work. And I'll do that both ways. So first, we know that through calculus, work is equal to the integral of force dx from the initial position to the final position. Now, we can write force again as force is equal to mass times acceleration, but this time we know that acceleration is derivative of velocity with respect to time, so acceleration equals dv dt. Now, we assume that mass is constant in this case, and we can rewrite this as work is equal to mass times the integral. I'm going to change the subscript initial distance to xi, and then xf here. So these being the same thing though. So mass times the integral of dv dt times dx here. Now, rearranging the infinitesimals here, we see that this is equal to mass times the integral of, I'm intentionally leaving the limits of integration out here for now, dv times dx over dt. So what we have done is moved the dt from the dv to the dx. And now we know that velocity is equal to dx over dt. So this is just equal to mass times the integral of velocity times dv. And this is a quite elementary integral. And so now, since we're integrating with respect to v, this is then the velocity at the initial position and the final velocity. So velocity at v at x final. So this is the final velocity. And now, integrating this, we see that work is equal to mass times 1/2 v squared evaluated from vi to vf. And evaluating this, we find that it is equal to 1/2 mvf squared minus 1/2 mvi squared. So vi squared. And this is equal to the difference in kinetic energy. So final kinetic energy minus initial kinetic energy, and then which is equal to the change in kinetic energy. So from this, we have shown that work is equal to the change in kinetic energy, even when there is even when there is not constant acceleration. So for cases with variable acceleration. Now we can show that the same principle applies even if we're starting off with kinetic energy. So we can write that kinetic energy here is equal to 1/2 mv squared. Now, if we take the derivative with respect to time of both sides, we find that dk over dt is equal to 1/2 m 2v times dv dt, because remember, you have to apply the chain rule since velocity varies with respect to time. Now, we know that acceleration is equal to dv dt, and substituting this in, we find that dk over dt here is equal to, also notice that 1/2 and 2 cancel here, so dk over dt is equal to mva. Now we know that force is equal to mass times acceleration, so dk over dt is equal to force times velocity. Now, moving the dt to the other side here, we find that dk is equal to force times velocity dt. Now, if we integrate both sides of this, we know that the integral of 1 dk from initial k to final k is equal to the integral from initial time to final time of force times velocity dt. Now recall that velocity is equal to dx over dt. So substituting that in, we have the change, so final kinetic energy minus initial kinetic energy, which is the left side of that equation evaluated is equal to the integral of force dx over dt times dt. And so dt here cancels out, and then we get that the change in kinetic energy is equal to the integral of force dx. And now we're starting at the initial position and ending at the final position. If you notice, this is the exact same as what we define work as. So this integral is equal to work. So now we have shown that the work energy theorem applies even if we work from kinetic energy and then work to work in cases with non-constant acceleration. And so this just proves that the work energy theorem holds through both algebra and calculus for cases with constant and variable acceleration. All right, thank you.